Curriculum for the study of geography. Premise. The study of modern geography implies the formation of some preparatory skills, such as the acquisition of the basics regarding the origin of the elements of which the cosmos is made up, the evolution of the universe, to then move on to the constitution of celestial bodies, stars, and planets, up to the appropriation of some fundamental notions of the Earth's origin. From then on it is possible to accompany the student to acquire, through the images, important geographical knowledge, observing the conformation of the Earth, with the use of satellite images. From the Big Bang to the origin of the Earth. With the help of beautiful images retrieved through the service of the Hubble telescope, it is possible to observe countless splendid celestial bodies, such as nebulae, constellations, formations of the universe, through which it is possible, by calling for the help of imagination and some graphic strategies, to reconstruct the whole genesis of the universe, from the Big Bang to the genesis of the solar system and the Earth. History of the universe. From Wikipedia, the free encyclopedia. According to the most accredited thesis in the scientific community, the history of the universe began with a theory published in 1927 explained by the priest and astronomer Georges Lemaître I, then supported and developed by George Gamow. According to this theory, the universe, during its birth, would have expanded from a point of infinite density by generating itself, a metaphor widely used, although improper, to describe this phenomenon is that of a colossal explosion. This phenomenon is called Big Bang, expression coined by Fred Hoyle in 1949 too. One of the pieces of evidence supporting this hypothesis is the diffuse radiation that still persists from the hypothetical beginning of the universe. The state of the raw material of the Big Bang cannot be described in physical terms, since it is in a state called singularity by physicists. George Gamow, on the strength of Friedmann's theory and that of Georges Lemaître concerning the primordial atom, hypothesized the idea of a great explosion, Big Bang, where the matter, being in extreme temperature and density conditions, caused the Big Bang, which led to the expansion and creation of today's universe. Also interesting is the theory of André Linde who conjectures after the fateful Big Bang, the formation of many universes, each one enclosed in itself inside a kind of bubble, within each of which different physical laws apply. This theory is called the multiverse. Today cosmologists are led to consider the theory of inflation, expressed by Alan Guth, as the one that best fits the observed reality, on the basis of today's discoveries and knowledge, starting from Gamow's theory, which inserts concepts from elementary particle physics, we arrive at a hypothesis, never made before, on what would have happened during the first second of the life of the universe, because little was known about the properties of matter at such extreme conditions. But Guth, starting from the research done by Stephen Hawking, theorized an extremely fast expansion process. Using the theory of gravitational fields, he thought that a region of that chaotic state began to inflate, hence the term inflation, so fast as to give rise to our universe. Timeline for the expansion of the universe. Ultimately, the accepted theory is the inflationary one, which sees at its origins a singularity that causes an explosion in a chaotic pre-universe, which in the first second expands very rapidly, and then continues more and more, in a process not slowed down enough by the force gravity of galaxies and the massive presence of dark matter. 13.7 billion years ago, the Big Bang takes place, which marks the birth of the universe, or rather, the beginning of its expansion through the birth of space-time. 4. Planck era. None of the current physical theories can correctly describe what happened in the Planck era, which was named after the German physicist Max Planck. In this era, the four fundamental forces, electromagnetic, weak nuclear, strong nuclear, and gravity, have the same strength, and are perhaps unified into a single fundamental force. Age of Grand Unification. Diameter of the universe. Temperature, 1030 K. Time after the Big Bang, 1/10 of a billionth of a yoctosecond, 10 to 43 seconds. Also called era of Gut. The fundamental forces, except gravity, were combined into a single superforce consisting of the electromagnetic force and the weak and strong nuclear forces. According to current knowledge, it is precisely at this moment that we can trace the birth of space-time as we know it. Age of Inflation. The same topic in detail, inflation, cosmology. Diameter of the universe, 1026 meters. Temperature, 1027 K, equal to a billion degrees C. Time after the Big Bang, 1/100 of a yoctosecond, 1035 seconds. In the age of inflation, swings in inflation gave rise to a rapid but drastic expansion of the universe. The energy in the form of radiation released by this particular Higgs field gave rise to particle-antiparticle pairs. Age electroweak. Diameter of the universe, 10 meters to 1012 meters, 1 billion kilometers. The universe has become enormously larger due to inflation. Temperature, 1027 K to 1015 K, equal to 1 million billion degrees Celsius. Time after the Big Bang, 100 millionth of a yoctosecond, 1032 seconds, to 1 nanosecond, or 10 seconds, 1 billionth of a second. In this era, the strong Higgs field had already separated the strong interaction from the electroweak one, resulting in the formation of gluons and quark-antiquark pairs from the radiation released following inflation. The X and Y bosons, if they ever existed, are hypothesized to have appeared in this era. The electroweak era lasted about 10-27 seconds. Its end was characterized by the separation of the electroweak force into weak and electromagnetic interaction, a phenomenon determined by the oscillations of the electroweak Higgs field. Age of leptons and antileptons. Diameter of the universe. Temperature 1012 K. Time after the Big Bang 10.4 seconds since the Big Bang. At this point in the history of the Earth is 1 billion degrees.
Slide 30.
Age of the hadrons. Diameter of the universe 100 billion kilometers. Temperature 1013 K, equal to 10,000 billion degrees Celsius. Time after the Big Bang 1 microsecond, 10^6 seconds, 1/millionth of a second. During the age of hadrons, thermal energy became low enough to allow for interaction between quarks by the strong force. Quarks and antiquarks thus bonded to form the first hadrons. Age of leptons and antileptons. Diameter of the universe. Temperature 1012 K. Time after the Big Bang 10.4 seconds since the Big Bang. At this point in the history of the universe, the temperature is about 1 trillion degrees. 1 second after the Big Bang, the temperature is 10 billion degrees Celsius. 100 seconds after the Big Bang, the temperature is 1 billion degrees. Age of nucleosynthesis. The same topic in detail, primordial nucleosynthesis. Diameter of the universe, more than 1,000 billion kilometers. Temperature, 1010 K. Time after the Big Bang, 100 seconds. In this era, most of the neutrons decayed into protons. The energy dropped enough to allow the nucleons to bind through pions, thus forming the first nuclei of helium-4 and deuterium. Age of opacity. Diameter of the universe, between 10 and 10,000 light years. Temperature, 108 K. Time after the Big Bang, 200 seconds. In this era, the energy dropped enough to allow the electromagnetic interaction to manifest. The charged particles interacted with each other and with photons left over from the inflation and annihilation of particle-antiparticle pairs. In this era there was the formation of the first atoms, above all of hydrogen, helium, lithium, and isotopes of hydrogen. At the end of the opacity era, the temperature dropped enough to reduce the production of massive generation quark-antiquark or lepton-antilepton pairs. See Standard Model. After the Big Bang. Age of Matter, Current Universe, edit Wikitext. Diameter of the universe, 100 million light-years. Temperature, 3000 kelvins. Time after the Big Bang, 300,000 years. In the age of matter, photons left over from the age of inflation spread throughout the universe, forming the cosmic microwave background that is also present in the present universe. All matter was mostly made up of first-generation atoms and leptons. All the massive particles which, with high temperatures, continuously formed particle-antiparticle pairs from radiation had already decayed into first-generation light particles, such as electrons and neutrinos and, among hadrons, neutrons and protons. The age of matter still lasts for about 13.7 billion years. 1 million years after the Big Bang, the temperature is 300,000 to 400,000 degrees Celsius. The first atom is formed, the hydrogen atom consisting of one proton and one electron. The formation of the first stars. The galaxy M101, one of the most beautiful examples of a spiral galaxy. The irregularities in the distribution of matter by the INFL atom were caused by quantum fluctuations in this particular Higgs field. Towards the beginning of the age of matter, irregularities manifested themselves above all in zones of matter that were more condensed than in others. The gravitational force acted on these irregularities, forming ever greater agglomerations of matter. This led to the formation of the first stars, 200 million years after the Big Bang, and the first active galaxies, mostly quasars. Astrophysicists hypothesize that the first stars formed in the universe were much more massive than the current ones. The nuclear fusion processes triggered in the nucleus of these stars led to the formation of heavy elements such as oxygen, carbon, neon, iron, and nitrogen, which spread throughout the interstellar space following the explosions of the stars in supernovae, resulting in the formation of black holes. 15.2 billion years ago, 500 million years after the Big Bang, He 1523-0901 was born, the oldest known star. With their explosion, the massive stars formed 13.5 billion years ago, called megastars, gave rise to electromagnetic radiation. Particularly intense electromagnetic radiation, probably responsible for the ionization of the hydrogen atoms found among the clusters of galaxies in the present universe. 12.7 billion years ago, perhaps, but it is one of the most discussed pieces of information in cosmology, the condensations of galaxies, protogalaxies, are produced and the formation of stars begins. 10 billion years ago, formation of our galaxy, the Milky Way.
Slide 37.
The acceleration of dark energy. The same topic in detail, universe in acceleration. About 7 billion years after the Big Bang, the universe, which was slowing its expansion due to gravitational force, as shown in Figure 4, experienced an acceleration in its expansion, which is still detectable in the present-day universe. This acceleration may have been caused by dark energy, the anti-gravity lambda force 5. This will likely lead the universe to end in a big rip or big freeze, unless dark matter and its gravity take over or dark energy is the exact explanation for the apparent acceleration. 5 billion years ago, the solar system was born and therefore also the star we call the Sun. 4.5 billion years ago, formation of planet Earth. 4 to 3.5 billion years ago, the first forms of life appear on 4.5 billion years ago, formation of planet Earth. Four to 3.5 billion years ago, the first forms of life appear on Earth. End of the universe. The same topic in detail, ultimate fate of the universe. Theories based on the Big Bang can be divided into three main groups. Those for which, despite the observations, the universe is eternal as previously thought, the steady-state theory and the oscillating universe, and its more modern variant, the Big Bounce. Those for which the universe had a beginning, but will not have a real end, the heat death of the universe and the Big Rip, Great Tear. Those for which the universe had a beginning, and will have a well-defined end, the Big Crunch. In cosmology, the Big Crunch is a hypothesis or cosmological model about the ultimate fate of the universe, which holds that the universe itself will stop expanding and begin to contract until it collapses on itself, exactly symmetrical to the initial Big Crunch. Bang.
Now we see the beautiful movie Home.
Listen to me, please. You're like me, a Homo sapiens, a wise human. Life, a miracle in the universe, appeared around 4 billion years ago, and we humans, only 200,000 years ago. Yet we have succeeded in disrupting the balance that is so essential to life. Listen carefully to this extraordinary story, which is yours, and decide what you want to do with it.